Hi, my name is Bo Zhang, and I would like to present an empirical study of tokenization strategies for various Korean NLP tasks, written by Gyubyung Park from Kakao Brain, Juhong Lee and Daun Jung from Pingpong AI Research, and Bo Zhang from Posttech. Our work covers the area of morphology and word segmentation in Korean. Here's the table of contents. First, I briefly introduce the motivation of this work and then present each token strategy we used in the whole experiments. Main results will be presented next. We conducted experiments on two representative tasks of NLP. The one is machine translation and the other is several kinds of natural language understanding tasks. After that follows analysis and discussion for the results. Then I conclude the presentation with a summary. Tokenization has long been studied since it is the first step of embedding the meaning of language in a vector space. There also has been undergoing research related to word segmentation itself in some languages, such as Chinese. Tokenization involves segmentation of big chunks into smaller units, such as words themselves separated by white spaces, characters, or other sub-level tokens defined by certain algorithms. Recently, a scheme inspired by byte-pair encoding algorithm, which is used to compress data, is widely used and proven to be effective across multiple languages. Korean is not an exception. BPE tokenizer became standard in both Korean machine translation tasks and most of recently proposed huge language models like Korean BERT or GPT. Yet, linguistically motivated approaches are also preferred in morphologically rich languages such as Hindi, Arabic, Latvian, along with Korean, due to the complex systems of inflections and conjugations. For example, a Korean word 먹다, which means eat in English, carries countless inflectional forms like 먹는다, 먹고, 먹어서, etc., whereas there exist only limited number of conjugations for word eat. So there have been some tries to take the best of both worlds that combine linguistics-based methods and statistics-based methods like BPE. But still, the effect of these methods is not thoroughly investigated for a Korean language. Based on these observations, we posed a research question: what is the best tokenization strategy for Korean NLP tasks? In this section, I present the tokenization strategies we used in all of the experiments one by one with a simple example. Here's an example sentence, 나랑 쇼핑하자, which means let's go shopping with me. The first strategy is consonant and vowel, where the most fine-grained segments are generated. In Korean, each syllable is composed of 2 or 3 consonants and vowels. In this scheme, each syllable is decomposed to become one token. Note that a white space in the row text turns into a separate asterisk token. It is because we have to recover a decoded sequence to the original sentence in some tasks like translation, which is usually called detokenization. Syllable strategy considers each character a token. It is the same as character-level tokenization. Morpheme strategy leverages off-the-shelf morphological analyzer. We used MeCap-Co, a Korean extension of CRF-based Japanese analyzer MeCap, to decompose each word into smaller units of morphemes. Each morpheme becomes each token. Suburb strategy takes advantage of BPE algorithm to segment words statistically. We used Google's sentence piece. Morpheme-aware suburb strategy is a combination of morpheme strategy and suburb strategy. Each morpheme in a sentence is segmented and separated by a white space, and then BPE training is conducted with these segmented sentences afterwards. By doing so, morpheme boundaries can be preserved. Word strategy is the most basic and coarse-grained one. Each word corresponds to each token. All punctuation marks are separated. Now I introduce evaluation results for two NLP tasks. The first one is machine translation. Recently, AI Hub released a massive parallel corpus for Korean to English translation and vice versa. The dataset covers documents collected from various sources, and we used news corpus in our experiments. The dataset consists of 800K instances in total. We split them by 98% for training and 1% each for validation and test, respectively. Before regular experiments, we had a question on which data to train BPE. There are two options. The first option is training data for machine translation itself. This gives an advantage that the token distributions of BPE model and the task-specific training data are the same. The other option is using Wikipedia corpus, which is about 5 times larger than the former. The result tells that there is no significant difference between the two in English to Korean setting, whereas the BPE model trained on the larger corpus yields 2 to 3 points better in BLUE score. According to this, we decided to train BPE tokenizers on Wiki corpus for all settings and tasks. The overall results are shown in the figure on the right side. The performance of word tokenizer collapses due to very high OV rates because it cannot reflect subword structure to construct vocab efficiently. This phenomenon is more prominent in morphologically rich languages. Likewise, morpheme tokenizers yield relatively lower BLUE scores than other groups, despite the power of linguistic knowledge. OV rates is a crucial factor that degrades performance unless maintained low enough. However, it is not the only factor that affects performance. Although consonant and vowel tokenizer has the lowest OV rates, its BLUE score is lower than more coarse-grained models such as syllable, subword, and morpheme over subword. We conjecture this is because a single token has to cover the vast range of contextual information. Overall, morpheme over subword tokenizers achieved higher BLUE scores than their equal-sized counterparts of the other groups. This table shows the number of tokens that cross morpheme boundaries in subword tokenizers. From this result, we can see that subword tokenizers cannot preserve meaningful units quite often. To sum up, realizing morpheme boundaries is also important. Thus, morpheme over subword tokenizers worked best for machine translation. The second experiment includes several NLU tasks. We conducted experiments for 5 tasks. Core dataset, a Korean version of SQuAD, is for machine reading comprehension, that is to predict answer span given a passage and a question. It consists of around 60K training set and 6K dev set. Since the test set is not open to public, we only report exact match and F1 scores for the dev set. Core NLI dataset, a Korean version of SNLI, MLNI, and Cross-NLI combined, is for natural language inference task, that is to classify a pair of sentences into 3 categories of entailment, contradiction, and neutral. It consists of about 940K training set, 2.5K for dev set, and 5K for test set. Core STS dataset, a Korean version of STS-B, is for semantic textual similarity tasks, that is to regress how similar two sentences are. It consists of 6K training set, 1.5K for dev and test set each. NSMC is a movie review dataset for sentiment analysis, that is to classify a review sentence into either positive or negative. It consists of 150K training set and 50K test set. We used 10% of training set as the held out dev set. The last one is POSE-CROSS, a cross-lingual dataset for paraphrase identification, that is to classify whether 2 sentences are paraphrases of each other or not. Korean portion consists of 50K training set and 2K for dev and test. We followed the common setting of pre-training and fine-tuning as other state-of-the-art frameworks. We used BERT base architecture with 12 transformer layers and 768 hidden dimensions, and pre-trained on the combined set of Korean Wiki and Namu Wiki, which amounts to 6 GB for 1 million steps in total. Then we added one additional fully connected layer to fine-tune each model. Detailed hyperparameters are described in the table on the right. Again, word model achieved the lowest scores across all tasks. Especially in core code, it is much worse than the other models because There are so many named entities closely related to answers that turned into the unknown token due to the capacity of vocab. Consonant and vowel model is the second worst by a quite large margin in most of the tasks, which is different from translation results, where the performance gap is relatively small. Syllable model recorded almost similar to morpheme models. Morpheme models again show clear tendency that larger vocab results in better performance. Morpheme over a suburb model with the largest vocab shows the best scores over all tasks except Core Quad and Core STS test results. In Core Quad, suburb model with the largest vocab achieves the highest in both exact match and F1 score. Now I suggest some analysis from the aforementioned results. First, we examine the effect of average token length and linguistic awareness on translation performance by comparison. The figure on the right illustrates blue scores with respect to the average syllables each token contains. Syllable, suburb, and morpheme or suburb models, which lie in the range from 1.0 to 1.5 average syllables per token, achieve relatively high blue scores, while the models with more than 1.5 average syllables show degraded performance. This indicates that a single token should not be too long to cover much information. Next, we compare the scores of suburb 8K and morpheme or suburb 16K model, where a token in two models bears almost the same amount of information in that they have the same average number of syllables. From the fact that a morpheme or a suburb model scored better, we can conclude that linguistic awareness affects performance. Here, we focus on the effect of undertrained tokens on translation performance. We name the tokens that appear in the training set for very few times undertrained tokens. The figure on the right illustrates the cumulative frequency rates of undertrained tokens with respect to the time of appearance. Understandably, consonant and vowel model and syllable model have almost zero undertrained tokens. Obviously, morpheme model suffers the most from undertrained tokens. Suburb model has larger amounts of undertrained tokens than morpheme or suburb model. We speculate undertrained token is also one of the factors that affect performance. So now I conclude the presentation here. We compared diverse tokenization schemes on two NLP tasks to answer the question raised, what is the best tokenization strategy for Korean NLP tasks? As a result, morpheme over suburb model with the vocab size of 32K performed the best in machine translation, and the same model with the vocab size of 64K performed the best in natural language understanding. It simultaneously appeared in both tasks that utilizing morphological structure when using BPE tokenizer can help. This is all for our work. Please refer to the paper and our GitHub repository for more details. Thank you for your attention.